Hi, Mr. Minnick here, helping my students learn BitString flicking so they can conquer the universe and cure cancer with zeros and ones, because that's what a bit is, a binary digit. So good old ACSL has these questions where we use the R shift or L shift, R circ. Hey, go read the guide that I have somewhere. It might be password protected in Schoology, who knows, um, uh, to learn how these work, or just basically YouTube it, and you'll see many people explain these. I'm going to just go straight to this question number one and work it out the way that it comes out of my brain. Well, you got to follow order of operations, and that means you got to work from inside the parentheses out. R shift 2, 1, 0, 0, 1, 1. So that means, that's the direction right. So bye-bye, see that 1 and 1? They're shifted off. Two of the bits, because of that 2, are shifted off. So don't say it's 100. That's not the number 100. That's the bit string 100. But you must always keep the length of a bit string the same. You can't drop leading zeros like you can in binary math or decimal math. It's used in a whole different way than normal numbers in math that you've learned. So you got to introduce zeros coming in from the left. So I've now evaluated that part. And if I had time in this video, I would copy everything. So I'm purposely showing bad style. Some of you put like your steps all over the place, and I can't like give you partial credit because I don't know what you're doing. Please show good steps. So I'm allowed to do ditto, and then all this is 0, 0, 1. Next, R circ 8. What? 8, but it's only a length of 5. Well, what's 8 modulus 5? 3. So that's really R circ 3. It's really R circ 3. Now you could do the 8 if you have extra time to walk around in circles. But let's just write circ 3, because the length of that bit string was 5. So see these 3 guys here to the right edge? They circulate around and come in from the left. The 0 peels off, the 0 peels off, and the 1 peels off. Guess what? It's basically like saying we have a 100, because we had a 100 here. We have a 100 here, but those 2 zeros are now here without the gap. So it's 1, 0, 0, 0, 0. Don't say the number 10,000. Now all of this right here is now simplified to 1, 0, 0, 0, 0. Now R shift 2. So bye-bye, those 2 guys. And the 1, 0, 0, I almost said 100. The 1, 0, 0 kind of shift over, and coming in from the left are 2 new zeros to keep the length at 5. So I did the answer for you. I didn't mean to go that far. Do not put the answer of just 1, 0, 0. You can't drop off these leading zeros. And that looks like a 6, but that would mean nothing because you can't have a hexanary computer. You can only have binary computers until we get to quantum computing, but I want to get into that. So there's the answer to number 1. Number 2. Oh, that's a typo. Oh, no, that's not a typo. Equals. Oh, this is tricky. So X is really a 5-bit length string. So let's put A, B, C, D in there as placeholders for the individual bits of X. And let's just think this out to some degree. And what we're ultimately doing here is coming up with the I would say ordered pairs, but we're finding pentuples that would plug in for X, or A, B, C, D, E, that would make this algebraic equation true. So look at this 1, for example, that 1. That 1 on a bitwise ordering relates to that 1 and that 0 and the E. And what's first according to order of operations, and or? And, because it's like multiplication, or is like addition. So really, I can simplify this part of the expression. So let's actually work from left to right. What's a 1 ANDed with a 0, Nathan? Too slow, 0. Second try, Nathan. What's that 0 bit ANDed with the second bit there? What's a 0 and 0? What's false and false? Good. What's a 1 ANDed with a 1? What's that 1 ANDed with that 0? Yeah, same thing as like 1 times 0. And that 0 ANDed with that 1 is 0. So basically, I've simplified the part of it that I can. And if you R shift 1 this, Bye-bye, E, you're gone. A, B, C, D, and because it's an R shift, we bring in a 0. Now we still have this OR, so we're basically asking what possible sets of bits could be a solution to A, B, C, D here that would make, well, 0 ORed with a 0 yields a 0. Good, that checks out. A, what plugged in for A when ORed with that 0 would yield this 0? It'd have to be a 0. A has to be a 0. And the E could be anything, so that E could be a 0 or a 1. So good luck finishing this question. You have to analyze the B and the C and the D and match them up with their corresponding bits here to see whether or not logically with the OR operation, you know what they would have to be or not be. And number 3, that's just straightforward simplification like number 1 was. Oh, look, not. The not of all that, flip all these 0s to 1s, light switch on off, and that 1 switches to 0. So I just did that part for you. And in number 4, go review hexadecimal numbers. Because really all numbers just change the bits behind the scenes in the computer anyway. And number 5, that's easy like numbers 1 and 3. So number 4 might be a little tricky, but I don't have time to make this video longer. So the proof is in the margin.